Okay, understanding diaphragmatic traps, bass traps, and testing. I entitled it this because this is a basic understanding of how diaphragmatic bass trap works and how we test it now based on what has happened in the past, which has not been exactly wonderful, and we'll go through that and talk about it. So the first thing I wanted to talk about was the different types of bass traps, because it's important to note that this testing doesn't necessarily apply to everything. Broadband bass traps, as you well know, thick fiberglass, mineral wool panels, things like that, used for broadband use. And it's not just for low frequencies, but it's usually to extend a panel to low frequency spectrums. We all know about 4-inch panels, 6-inch panels, things like that. That's common. This really isn't dealing with that. Helmholtz. This is a possibility to be used for Helmholtz as well, because for those who don't know what Helmholtz is, it's holes typically in wood plates tuned by size and spacing. It's a theory that's been around for literally hundreds of years, and was used by the Romans back in the day. So that's a whole nother animal. Composite traps. This probably can't be used for those either, although it potentially the low frequency performance of a composite could technically be used. These are typically fiberglass or mineral wool with assorted films and substrates in between them to, again, extend low frequency response. What we are talking about here is diaphragmatic, and a diaphragmatic bass trap, as you know, but many may not, is one that has a stiff front plate and interior spring treatments to adjust for frequencies, which is also based on depth, width, height. All kinds of different calculations go into diaphragmatic bass traps to make them perform at the various frequencies that we want them to perform at. So ASTM C423 and ISO 354 are the two standards in the world for testing absorption of acoustic products. Unfortunately, these do not address anything below 100 hertz. In fact, C423 is technically supposed to be between 125 and 4K, which really goes back to the old telephone days and why why we are so limited. But it's because we're testing in a diffuse field. Everything about C423, which I'm on the committee for that, and for the E33 committee for the United States, is all about the diffuse field and creating a diffuse field in the middle of a room. Again, as we were talking about, I don't like impedance tube testing. I don't trust it. It can probably be trusted maybe above 150 hertz to some extent, but for low frequency, I just don't believe it can be trusted. Right. That's a personal thing, and there will be those who would disagree with me, and that's perfectly fine. So it's about understanding modal zones. So everybody understands, for the most part, that when we talk about low frequencies, we're talking about modes and how to control the modes in a room. So as an example, we did a modal visual of my lab, our lab here at RealAcoustix, and this is at the various frequencies. These are technically the overlapping frequencies of the design nature of the lab. So you can see we've got 20, 30, 41, 43, 60, and 62. I just picked these out as examples to show what can happen, how the changes in the modes in a room happen depending on frequency. So if you look at number 1 in the upper left-hand corner, that's 20 hertz, and you can see the red represents a lot of effectiveness or efficiency in that frequency. It's all against the walls. And, as you move up, it can change pretty dramatically depending on the frequency. As you go up to 30, you see it becomes less efficient in the middle, but still very efficient in the corners of the room. Same thing with 41. Now it floats back to being on the walls. The walls are typically always going to be the most modal spots in there, and if you look at look at 41, you look at mode 4 versus mode 5. and you look at the way that it switches, with only a 2 hertz difference, it'll switch back and forth. You can't control what it's going to do, but the important thing to note is if you look at the middle of the floor on all of these, the most you might see is some modal response in those frequencies in stripes or in small zones of the floor, but they're always going to be against the walls. And this is what led us to really saying, okay, we need to test, since these devices in situ are installed on walls and corners. That's where we need to be testing it, because that's where the modes are. In a reverberation chamber, we specifically, for instance, the C423 standard, it specifically states you cannot test any products beyond 0.75 meters from the wall. And in the case of our lab, it's 1 meter from the wall. And because you can't create a diffuse zone that close to the walls, so we come out. So just the opposite applies for testing low frequency. We want to be in the modal zones, not in the diffuse field, because the diffuse field doesn't give us appropriate information, as you will see. So this is an experiment we ran with our 3248 model, which is 32 inches by 48 inches. And this particular model is, I think, was the 8-inch thick model. So and this is an A mount, a typical A mount test. And you can see that they are in the diffuse field of the lab. They're all mounted close together. In this case, I'll say it's too close together, because now we get sympathetic response from these. An example of this, I always like to point out, there's a manufacturer that builds a 2x2 device. And they tested 18 of them put together in an A mount like this. And they make a claim that the device can go down to 40 hertz. Well, first thing is that the waveform is way too large for a 1 or even 2 2x2 devices to have any efficacy at 40 hertz. Just can't happen. It's logic that those waveforms are too big. But also, by testing them all together, you would get some sympathetic response. And it wasn't very efficient. I think it was like a 0.6 NRC or something like that. But it's misinformation, and that's the thing we're trying to get rid of is bad information. So the other factor that comes in is you get edge diffraction. As we can see here, there's big edges in this particular model, and it creates a really interesting response. So this is what that test looked like. So the 63 hertz is correct. That is actually the center frequency. It's at a 1, which, but it's really, really narrow. It's a very narrow response. Yeah. The other thing is you come up with this interesting 40 hertz at about a 0.55, which technically shouldn't be there. Whether that was caused by the edge effect or whether it was caused by the mounting, or who knows what, it's really hard to say. It could be the coupling effect of all of them together as well. But that shouldn't be there. That's just an anomaly. And there's a lot of different things that you look at, even that slight slope up, which is not that slight. When you get a 10K, it's at a 0.5. We know the bass trap is not doing that. It's right. So all of these things led us to go, there's got to be a better way to do this. There's got to be some more coherent information in ways we do this. So we started to test against the walls, and we take this happens to be the 5-inch model of the BassMod 4848. And in the first test that we did, when we started to test against the wall in the modal zones, we start to see that it's performing a little bit differently. Now, obviously, this is a thinner unit, and again, the thickness can make a difference in the center frequency, which is really what where we concentrate on. But also we see this 80 hertz bump. We see 2 bumps. There should not be 2 bumps in a diaphragmatic absorber, and not to mention the third bump at a 0.5 at 40. All of these things start to make us go, why are we getting all this weird information out of these things. Again, what we found ultimately is that the units were too close together. Again, causing edge diffraction, which will cause, it could be a cause of either the 40 or the 80 there. The units are not flush to the wall because of that 3/4 inch conduit behind them. We couldn't go flush like that. And that creates a different pressure behind the unit. And then they're, again, too close to the corners. We found being too close to the corners also made a difference in the performance and how they reacted. So what we started to do is we began, I took them and I said, we got to tilt these. So we get rid of the back pressure behind it, because now it's an open space behind them. We're still well in the modal zone, so it's not a problem. And by doing this, now all of a sudden, I mean, we start looking at, okay, here's the performance, and we separated them by more than 1 meter apiece. And that made a world of difference. And it's really interesting because you would think that being closer together would actually increase the performance of the units. It did not. What it did was it actually created a test data that shows us what the individual units are doing by themselves, which actually makes them more efficient. And and very few people use bass traps coupled together. Once in a while here and there that you might see that, but bass traps are typically, you put one in one corner, one in another corner on a wall, on either the separated, one left, one right, that kind of thing, because that's appropriate. That's where they should be. And so we find out, all of a sudden that, when we do this testing properly, now we start to show what the efficiencies really are. And it gets, it really reduced the upper frequency issues, which again, I think were caused by diffraction, practically eliminate anything below the center frequency. It was really a, eye-opening experience for us to be able to really now see how these units can perform individually when tested properly.
Yeah.
So, this is the one I was telling you about, that the BassMod 2448 was the first model where where it came up with that left result that you see there. This is them mounted together in the corner, which is a very weird response. It's, we wish we could create, ones that could have that kind, if we could control that and say, okay, I want to get 50 hertz and I want to get 80 hertz and I want, all that would be, it'd be right. Nice, except those big dips are it'd be great for somebody that had that problem, but it's disingenuous, doesn't really work. So when we separated them out, now all of a sudden we have much better efficiency, still a slight bump in the 0.5. And again, I think that was simply because we had them too close together. We hadn't separated them by that 1 meter yet. And, but once we do, and you can see in subsequent tests, once we figured out that we needed to keep them more separated, this is really close to accurate, that right hand. But once we just needed to separate them a little bit more so that we didn't get the diffraction effects. So now when, this is more like it. So when we get to the 3248 8-inch, which you saw earlier in that A mount testing, which was only at a 1 at best, and then had that 40 hertz spike and things like that. Right. Now look what it does when mounted properly. Yeah, that's phenomenal.
Sweet.
Yeah,
that's what we're looking. Yeah, that's what you're looking for. Yeah,
and that's what we're looking for. And again, my whole perspective on testing and creating bass traps is it's surgical. I'm not looking to make something that goes out to 5K or something. This is about being able to create under 125 hertz, being able to create a device that I can tune anywhere you want to, anything, any place that you want it to be, from 40 hertz all the way up, even below 40 if we wanted to, although they get awfully big when we do that. But, from 40 hertz to 125, we can literally, create any frequency that we want to now. We've tested that many devices and that many different spectrums and sizes. And the other thing is size. From a pragmatic standpoint, not every room can hold a 4848 or 4896, for instance, things like that. It's really important to note that we have a lot of different sizes so that they can fit into the environment, including corner modules and things like that. And and we can adjust to a certain extent. We can adjust the frequency spectrum and figure out here's what we need to do in order to get there. And it's so that's really, it's been the thing. And the other thing was to create both narrow and broadband. For instance, this one that you see here is a narrow band. So and we get a lot of customers say, I've got real issues at 63. So here we go. The BassMod 3248 will take 63 and just basically kill it. So which is what you're looking for. But then if we want to do a broader module, we have that capability as well through some other creative methodologies that we've used in the design of the units, that allows us, in this case, to go from 50 to 100 with quite a bit of efficacy. You're looking at 1.5 and up to 100 at 1.33. So that's beyond anything that we've ever seen before. And and I think that anybody else can offer. It's really having that capacity, and then having it drop off quickly. As you can see, it's down to a 0.3 at 200 hertz. So it's really not dealing with anything in the other ranges that typical panels, fabric wrap panels, things like that, can handle. So that's and that was the goal. That's been the goal for the last 3 years that we worked on this. So the some important notes to make, and this isn't for you necessarily, John, as it is for the person who may not be as attuned or as educated in this work. These experiments were conducted to create a proper method for testing diaphragmatic bass traps. And again, like I said, I think the only other one that could be tested this way, but time will tell, we'll see, is probably Helmholtz bass traps, because they're going to work on somewhat the same principles with pressures. The idea here is, especially since Ron and I are both on the ASTM C423 committee, is to be able to present some cogent information as to including this as an addendum to C423 for testing low frequencies.
Need to get these things pushed through. I hope that Ron can finish his papers and get them published there, get it accepted. It just takes a long time.
Yeah, I think it's a slow process. I'm hoping that we have enough information, because I'm going to be doing a paper on it as well and presenting this information. I think we have enough information here to not make it too difficult for them to say, yeah, let's move forward on this, because otherwise they'll continue to test in the wrong way, and that I don't think they want that either. So it'll be interesting to see what kind of commitments we can get from the committee, and we'll be presenting it at this next meeting. So